Every electricity generation technology has advantages and disadvantages. For example, renewable technologies such as solar and wind do not produce greenhouse gases but are not always available when needed and can require significant amounts of land. On the other hand, technologies such as coal and nuclear can produce electricity in large quantities reliably around the clock but can result in significant greenhouse gases when unabated in the case of coal or long-term waste disposal considerations in the case of nuclear. Understanding these trade-offs among generating technologies reinforces the importance of having a diverse generation technology portfolio for reducing greenhouse gas emissions while economically and reliably meeting electricity demand. When applied as part of an integrated portfolio, all generation technologies can play useful roles that capitalize on their strengths. This video explores some of the advantages and challenges of both current and emerging electricity generation technologies when comparing attributes including cost, availability and operational capabilities, and environmental considerations. It presents a comparison of technologies at a high level, followed by a more detailed explanation for the assessment of each parameter analyzed for each technology. While the assessments represent the general characteristics of the technologies evaluated, the exact details of many parameters will be unique to the site, region, and/or country in which the technology is being considered. Furthermore, the details around the costs and capabilities of emerging technologies are less certain than those of generation technologies that have been mature and commercialized for decades and reflect expectations more than demonstrated capabilities. Now we will talk about CCS, carbon capture and storage. CCS is a vital technology that plays a significant role in mitigating the impacts of climate change. As the world continues to rely on fossil fuels to meet its energy needs, the emissions of carbon dioxide and other greenhouse gases continue to rise, leading to global warming and other environmental concerns. CCS is a process that captures carbon dioxide (CO2) emissions from power plants and other industrial sources before they are released into the atmosphere. The captured CO2 is then transported and stored underground in geological formations such as depleted oil and gas reservoirs or saline aquifers. This process prevents the carbon dioxide from entering the atmosphere, thereby reducing the impact of greenhouse gases on climate change. The technology behind carbon capture and storage is relatively simple. The CO2 is first captured through a process known. Now come to conventional nuclear. Construction cost. Construction costs for nuclear plants are relatively high compared to other options because of the complexity of the designs, the robust facilities needed to provide safety, and the redundancy built into nuclear plant designs. Electricity cost. Electricity production costs for new nuclear plants are moderate over their projected lifetimes because of low fuel costs and the near-continuous operation of nuclear plants, resulting in a large amount of electricity generated, offsetting their high capital costs. Capacity factor. Nuclear plants have the highest capacity factor of all generating technologies. They typically operate around the clock, 4 months at a time, often going 1 to 2 years between outages. Ramping capability. Nuclear plants have historically tended to operate at full power for best efficiency and lowest cost generation. However, they can operate at reduced power, allowing for some flexibility and ramping capability. Following an outage, several hours to several days are required to start up the plant, depending on the reasons for the outage. Availability. Nuclear plants are extremely reliable sources of electricity. They typically operate around the clock, 4 months at a time, often going 1 to 2 years between outages. Refueling and maintenance outages are scheduled during low demand seasons in the spring and fall. Total area use intensity. Nuclear plants have a relatively small plant footprint for the generating plant and its supporting facilities for a given capacity. The significant amount of energy released during fission results in fewer uranium mines and lower land use mining. Nuclear power plants require large amounts of water for operations, mostly to cool the steam that powers the turbine generators to generate electricity. Because nuclear plants generate electricity from the energy released during the fission process, no combustion is involved. Unlike fossil plants, therefore, there are no GHG emissions. Although radioactive emissions from a nuclear plant are possible in the event of an accident, emissions of other gases and pollutants are negligible from nuclear power production. Compared to waste products from certain other generation technologies such as coal plants, waste volumes associated with nuclear are very small. However, the toxicity of these waste products, particularly used nuclear fuel, remains high for many years, and careful handling, storage, and long-term disposition is essential. In order to build a nuclear plant, a country must have a regulatory framework in place. Even with the framework present, it can take several years to acquire all the permits for operation of a nuclear power plant. Nuclear plants will require considerable resources to remediate the plant site for future use. Nuclear waste will require long-term monitoring storage after plant decommissioning. Now come to small modular reactor SMR, which includes small modular light water reactors. It's another emergency technology coming to service. Construction cost. Construction costs for SMRs are expected to be lower than large-scale nuclear due to reduced complexity and advanced safety designs, but are still relatively high compared to other technology options. Electricity cost. Electricity production costs for new SMR plants are moderate over their projected lifetimes because of low fuel costs, high plant output, and potential revenue streams from co-products in addition to electricity. Capacity factor SMRs can have similar capacity factors as conventional nuclear. Ramping capability. SMRs inherently have the same ramping flexibility as conventional nuclear reactors. Availability. SMRs will have similar availability as conventional nuclear plants. Total area use intensity. SMRs have a relatively small plant footprint for the generating plant and its supporting facilities for a given capacity. The significant amount of energy released during fission results in fewer uranium mines and lower land use mining. Direct water use intensity. SMRs require large amounts of water for operations, mostly to cool the steam that powers the turbine generators to generate electricity. Because SMRs generate electricity from the energy released during the fission process, no combustion is involved. Unlike fossil plants, therefore, there are no GHG emissions. Although radioactive emissions are possible in the event of an accident, emissions of other gases and pollutants are negligible from SMR power production. Direct waste for SMRs is comparable to conventional nuclear. The application, review, and approval process for SMRs can be similar to nuclear, but pre-approvals and inherent safety features of these plants may expedite the process. SMRs will have similar end-of-life considerations as conventional nuclear. Slide 9.